Everything we thought we knew was wrong. When the James Webb Space Telescope turned its golden eye toward the edge of time itself, peering back across 13.5 billion years of cosmic history, it did not find what we expected. It found something impossible. Something that challenges the very foundation of our understanding. The universe, in those first fragile moments after its birth, was not supposed to look like this. Imagine opening a time capsule buried at the dawn of existence, expecting to find primitive tools and crude beginnings, only to discover intricate machinery, sophisticated architecture, complex civilizations already thriving when they should have barely existed at all. This is not metaphor. This is what happened. The telescope revealed galaxies, vast and mature, glittering in the cosmic dawn like impossible jewels, galaxies that according to everything we knew, every equation we trusted, every model we built over decades of careful observation, simply could not be there. How do you reconcile what you see with what you know must be true? How do you hold in your mind two contradictory visions of reality and accept that one of them, perhaps the one you've spent your entire career defending, might be fundamentally mistaken? These are not abstract questions for philosophers debating in comfortable rooms. These are urgent, immediate questions that astronomers and physicists are grappling with right now, in this moment, as data streams down from that telescope suspended 1,000,000 miles from Earth, data that refuses to conform, refuses to behave, refuses to let us rest easy in our certainty. The story begins, as so many stories do, with confidence. For nearly a century, we have told ourselves a particular story about the universe, a narrative so compelling, so well supported by observation and mathematics, that it became more than theory. It became truth. The Big Bang, we said with certainty, was the beginning of everything. Not an explosion in space, but an explosion of space itself, a moment when all the energy and matter that would ever exist burst forth from a singularity so small, so dense, that our minds cannot truly grasp it. From that first instant, the universe expanded, cooling as it grew, matter condensing from pure energy, first into the simplest elements, hydrogen and helium, then gradually, over eons, into the complex tapestry of stars and galaxies we see today. This story had order. It had progression. It had a timeline that made sense. In the beginning, there was simplicity, chaos, formlessness. Then, slowly, painstakingly, structure emerged. Small galaxies formed first, we believed, small clumps of stars held together by gravity, and these small galaxies merged and collided over billions of years to create larger ones, and those larger ones merged to create larger ones still, until finally, after vast stretches of time, you arrived at the majestic spiral galaxies like our own Milky Way, the elliptical giants, the complex structures we observe in the modern universe. Think of it like watching a city grow. In the beginning, there are scattered settlements, primitive and small. Over centuries, they expand, merge, become towns, then cities, then metropolises. You don't expect to find Manhattan in the year 500 AD. You don't expect to find Dubai rising from the desert before humans even lived in that region. The progression is logical, predictable, hierarchical. Small things first, large things later. Simple before complex. This is the natural order of growth, of development, of evolution itself. And we had evidence. Mountains of evidence. Observations from the Hubble Space Telescope showed us this progression beautifully. Look back in time, Hubble told us, and you see galaxies that are smaller, less organized, more chaotic. Look further still, and they become even more primitive. The story held together. Every new observation seemed to confirm it. The universe, we concluded, built itself from the bottom up, a slow construction project spanning billions of years, following rules we could understand, equations we could write down, processes we could model in our computers. But here is what we forgot. Or perhaps what we never truly acknowledged. We were seeing the universe through limited eyes. Hubble, magnificent as it was, revolutionary as it proved to be, could only see so far. Its vision was bounded by the capabilities of its instruments, by the wavelengths of light it could detect. Like trying to read a book through a fogged window, Hubble gave us glimpses, suggestions, outlines of what lay in the deepest cosmic past, but never the full picture. Never the complete, unvarnished truth. James Webb was designed to see what Hubble could not. Built to observe in infrared wavelengths, to peer through the cosmic dust and across the vast distances that stretch and redden light from the early universe, Webb was meant to show us the first galaxies, the first stars, the first moments when light began to illuminate the darkness. We expected to see infancy. We expected to see the universe taking its first tentative steps. We expected confirmation of our beautiful, logical, hierarchical story. What we found instead was maturity where there should have been youth. We found complexity where we expected simplicity. We found galaxies so large, so well-formed, so seemingly evolved that they appear to violate the very timeline we constructed. These are not the small, primitive structures we predicted. These are massive galaxies, some approaching the size of our own Milky Way, glowing bright and defiant in an epoch when, according to our calculations, they should not exist at all. Consider what this means. Light from these galaxies has been traveling toward us for over 13 billion years. It left those galaxies when the universe itself was only a few 100 million years old, a mere infant in cosmic terms, barely out of the dark ages that followed the Big Bang. In human terms, this would be like finding a newborn baby who already has teeth, can speak in complete sentences, has learned to read, and is contemplating philosophy. It is not just surprising. It is impossible according to the developmental timeline we understand. The numbers are staggering. Where we expected galaxies to have masses of perhaps 10 million or 100 million times that of our Sun at this early epoch, we found galaxies with masses 10 times larger, 100 times larger, galaxies that appear to contain billions of stars already. Where we expected to find small, irregular blobs of light, we found structured disks, clear signs of organized rotation, evidence of processes that we thought took billions of years to develop. The timeline doesn't work. The math doesn't add up. The universe appears to have grown up far too quickly. How could this happen? How could galaxies form so fast, so efficiently, so completely in such a short span of cosmic time? After the Big Bang, the universe was nearly uniform, a hot soup of particles and radiation with only tiny variations in density, small ripples in the fabric of spacetime that would eventually become the seeds of all structure. Gravity, working on these tiny overdensities, would slowly pull matter together, and as matter accumulated, it would pull more matter, and eventually you would have enough mass concentrated in one place to ignite stars. Stars would live and die, creating heavier elements, and subsequent generations of stars would form from this enriched material, and gradually, over vast periods of time, you would build up the stellar populations that comprise mature galaxies. This process has a speed limit. Gravity, for all its relentless power, takes time to do its work. Stars take time to form, time to live, time to die. You cannot rush cosmology. You cannot speed up the fundamental processes of star formation and galactic assembly. Or so we thought. Or so every simulation we ran, every model we constructed, every careful calculation suggested. The early universe should be dominated by small galaxies, proto-galaxies really, messy and incomplete and still very much under construction. Instead, we are seeing finished products, or something very close to finished products, appearing on the scene far too early. What does this mean for our story? What does this mean for the confident narrative we have been telling? At minimum, it means we have seriously underestimated something. Perhaps we don't understand star formation as well as we thought. Perhaps stars could form far more rapidly in the early universe than our models predict. Perhaps the conditions in that ancient epoch, so different from anything we observe locally, allowed for processes that we have never witnessed, never imagined. Perhaps our assumptions about how gas cools and condenses and ignites into stars are wrong, or at least incomplete. Or perhaps, and this is where the ground begins to feel less stable beneath our feet, perhaps the problem is deeper than star formation. Perhaps our understanding of how galaxies themselves assemble is flawed. We have believed in this bottom-up model, this hierarchical assembly where small structures merge to form larger ones, but what if that is not the only way, or even the primary way, that galaxies formed in the early universe? What if, under certain conditions, under the unique circumstances of the cosmic dawn, galaxies could form quickly, all at once, massive structures condensing directly from the primordial gas without needing to go through the slow merger process we observe in later epochs? The implications ripple outward like waves from a stone dropped in still water. If galaxies formed faster than we thought, then star formation must have been far more efficient than we calculated. If star formation was more efficient, then the early universe must have been enriched with heavy elements more quickly. If heavy elements appeared sooner, then the conditions for planet formation, for chemistry, for the potential emergence of life, all happened earlier than we imagined. The entire timeline of cosmic evolution shifts, compresses, accelerates. But there is something else lurking in these observations, something even more profound and more unsettling. These galaxies we are seeing, these impossible objects shining at the edge of time, they are not just large. They are bright. Extraordinarily bright. Brighter than they should be given their mass and age. This brightness suggests something about the stars within them, about their populations and their characteristics. It suggests perhaps that stars in the early universe were fundamentally different from stars today. We know that the very first stars, the ones that formed from the pristine hydrogen and helium left over from the Big Bang before any heavy elements existed, would have been strange and exotic by modern standards. Without heavy elements to cool the gas efficiently, these first stars would have been enormous, perhaps hundreds of times more massive than our Sun, burning hot and bright and fast, living brief, violent lives before exploding as supernovae and seeding the universe with the first carbon, oxygen, iron, all the elements necessary for complexity and life. We call these population 3 stars, and we have never observed one directly. They existed too long ago, lived too briefly. By the time we look at any galaxy, even the earliest galaxies Hubble could see, those first stars are already gone, replaced by subsequent generations. But perhaps Webb is showing us their afterglow. Perhaps the brightness we see in these early massive galaxies is the signature of these exotic stellar populations, or at least of stars very different from what we find in the modern universe. Perhaps we are finally glimpsing the epoch when the universe transitioned from pure simplicity to the rich complexity we inhabit, and that transition was not gradual and smooth as we imagined, but rapid and explosive and transformative. Every new piece of data from Webb seems to deepen the mystery rather than resolve it. Astronomers have found galaxies at redshifts that push even closer to the Big Bang, galaxies whose light has been stretched by cosmic expansion to such extreme wavelengths that we are looking back to when the universe was only 200 million years old, only 150 million years old. Each time we think we have seen the earliest galaxies, we find earlier ones. Each time we push the boundary back, we find that even at these absurdly early times, galaxies exist, and they are not always the small, faint, primitive objects we expected. There are galaxies that appear to be forming stars at prodigious rates, creating stellar mass at speeds that seem to defy the available supply of gas. There are galaxies with structures that suggest they have already experienced multiple generations of star formation, cycles of birth and death that should require far more time than the universe has had. There are galaxies whose spectral signatures indicate the presence of elements that should not yet exist, heavy elements that require multiple generations of stars to produce, yet here they are, abundant and present when the universe is still in its infancy. The cosmological community finds itself in an unusual position, one that is both exhilarating and uncomfortable. Exhilarating because we are seeing things no human has ever seen before, because we are touching the edge of the observable universe with unprecedented clarity, because every day brings new images, new spectra, new data that reveals the cosmos in ways we could only dream about before. But uncomfortable because this data is not behaving. It is not confirming our models. It is challenging them, contradicting them, forcing us to confront the possibility that we have been missing something fundamental. There are papers being written with titles that include phrases like crisis in cosmology, and tension with standard models, and unexpectedly massive galaxies. There are conferences where senior scientists who have spent decades building the theoretical framework of galaxy formation stand up and admit that they did not predict this, cannot easily explain this, need to go back to the drawing board. This is not how science usually proceeds. Usually, new observations fit neatly into existing frameworks, adding detail and nuance but not appending the foundation. What we are experiencing now is different. This feels like a moment of genuine revolution, of paradigm shift, the kind of transition that happens perhaps once or twice in a generation when our fundamental understanding of the universe must be revised. And yet, we should be careful not to overstate the crisis. The Big Bang itself is not in question. The expansion of the universe is not in doubt. The basic cosmological framework, the laws of physics as we understand them, these remain solid. What is being challenged is our specific understanding of how structure formed within that expanding universe, how quickly complexity could emerge, how efficiently matter could organize itself into galaxies and stars. These are important questions, crucial questions, but they are questions within a framework, not questions about the framework itself. Or are they? Because there is a darker possibility lurking at the edge of these observations, a possibility that some scientists are beginning to whisper about even though it seems almost too radical to consider seriously. What if the problem is not just with our models of galaxy formation? What if the problem goes deeper, into cosmology itself? What if some of our fundamental assumptions about the universe are wrong? We have built our cosmological models on certain pillars, certain constants and parameters that we measure and plug into our equations. The rate of cosmic expansion, the density of matter and energy in the universe, the strength of the initial fluctuations that seeded structure formation. What if one of these parameters is not quite what we think? What if dark matter, that mysterious substance that we know exists only through its gravitational effects but have never directly detected, behaves differently than we assume? What if there is some unknown physics, some interaction or force that operates at these extreme early times and scales that we have not accounted for? Dark matter is already strange enough. We know it exists because galaxies and clusters of galaxies move in ways that cannot be explained by the gravity of visible matter alone. There must be something else there, something invisible, something that interacts with normal matter only through gravity. We have given it a name, dark matter, and we have built detailed models of how it behaves, how it clumps together, how it forms the scaffolding upon which galaxies grow. But we do not know what it is. We do not know if it is one type of particle or many. We do not know if it has properties beyond what we have assumed. What if dark matter could collapse into dense structures more quickly than our models predict? What if there are mechanisms for dark matter to interact with itself or with normal matter in ways that would accelerate structure formation? Some physicists have proposed that dark matter might not be perfectly cold, that is, moving slowly enough to clump together on all scales. Maybe it has a small amount of warmth, some residual velocity that would affect how it structures itself on small scales while still allowing the large-scale structure we observe. Others have suggested that dark matter might interact with itself through forces we don't understand, dark forces acting only on dark matter, creating dynamics that could change how quickly halos form and how efficiently they pull in normal matter. These are speculative ideas, unproven, but the observations from Webb have given them new life, new urgency. Then there is dark energy, even stranger than dark matter, the mysterious force that is causing the expansion of the universe to accelerate. We have measured this acceleration, confirmed it through multiple independent methods, but we do not understand what causes it. Is it a property of space itself, a cosmological constant as Einstein once proposed and then abandoned? Or is it something more dynamic, something that changes over time, a field that has different strengths at different epochs? If dark energy behaves differently in the early universe than it does today, that could affect the rate of structure formation, the competition between expansion trying to pull things apart and gravity trying to pull them together. These are deep waters we are wading into, questions that touch the foundations of physics itself. And perhaps that is appropriate. Perhaps we should not be surprised that when we push our observations to the absolute edge of what is possible, to the very beginning of time itself, we encounter mysteries that require us to question our deepest assumptions. The universe has surprised us before. It will surprise us again. But let us return to those galaxies, those bright defiant structures shining in the cosmic dawn, because they are not just puzzles to be solved. They are also revelations, windows into an epoch of the universe that we have never witnessed before. Even as they challenge our theories, they are teaching us something profound about how the cosmos evolved, how it transitioned from the simple uniformity of the Big Bang to the rich tapestry of stars and galaxies and planets and life that we see today. One of the most striking findings from Webb is the sheer diversity of galaxies in the early universe. We expected uniformity, a population of similar small objects all going through roughly the same processes. Instead, we see variety. There are some galaxies that do appear small and primitive, exactly what we predicted. But there are also these massive outliers, and there are galaxies with strange shapes, odd colors, unusual properties that don't fit into neat categories. The early universe was not a uniform assembly line churning out identical products. It was a period of experimentation, of diversity, of different environments and conditions producing different outcomes. This diversity tells us something important about the randomness and unpredictability inherent in cosmic evolution. Yes, there are laws of physics, universal constants, equations that govern how matter behaves. But there is also contingency, chance, the particular arrangement of matter in one region versus another, the timing of when the first stars formed, the specific history of mergers and accretion that each proto-galaxy experienced. The universe is deterministic in its physics but stochastic in its outcomes. No two galaxies followed exactly the same path. No two regions of space had exactly the same history. We see evidence of this in the way galaxies are distributed across space even at these early times. They are not uniformly spread. They cluster, forming protogroups, early versions of the galaxy clusters we see in the modern universe. The web-like structure of the cosmos, the filaments of matter separated by vast voids, was already beginning to take shape barely a few 100 million years after the Big Bang. The gravitational pull of overdense regions was drawing matter toward them, creating rivers of gas and dark matter flowing along the filaments, feeding the growing galaxies at the intersections. This clustering is important because it affects how galaxies grow. A galaxy sitting alone in a void has a very different evolutionary path than one sitting at the intersection of multiple filaments where it can accrete matter rapidly from all directions. A galaxy in a group where it is likely to collide and merge with neighbors evolves differently than one in isolation. The environment matters. Context shapes destiny, even for galaxies. Webb is also revealing something unexpected about the gas in these early galaxies. When we analyze the spectrum of light coming from them, we can identify the chemical elements present in that light, and we can measure their abundances. In the very earliest galaxies, we expected to see almost pure hydrogen and helium, the primordial elements from the Big Bang, with perhaps the tiniest traces of heavier elements from the first generation of stars. But in many of these galaxies, we see significant amounts of carbon, oxygen, nitrogen, elements that require multiple generations of stars to produce in abundance. This presents yet another timing problem. If these heavy elements are present, that means stars have already lived and died, enriching the gas with their processed material. But how many generations of stars does this require? How much time? The universe at this epoch is only a few 100 million years old. The most massive stars, the ones that live fast and die young, enriching the universe with their supernova explosions, have lifetimes of only a few million years. So in principle, you could get several generations even in this short time span. But you need to form the stars, wait for them to die, have the enriched material mix into the surrounding gas, form new stars from that enriched gas, and repeat. The timing is tight. Very tight. Some astronomers have suggested that perhaps star formation in the early universe was not continuous but came in bursts, intense periods of activity where many stars formed rapidly, lived their short lives, and exploded, creating a sudden pulse of heavy elements. These starbursts would light up a galaxy brilliantly for a brief period and then fade as the supply of gas was exhausted or blown away by the energy from supernovae. If this is true, then the galaxies we see might be caught in one of these bright bursts, and we are not seeing their typical state but rather a special moment of intense activity. This idea of bursty star formation changes how we think about galaxies as objects. We tend to imagine them as relatively stable systems, steadily forming stars over long periods of time, evolving slowly and predictably. But perhaps, especially in the early universe, they were much more dynamic, experiencing dramatic swings between periods of intense activity and periods of quiescence. A galaxy might form a large population of stars very quickly, then go quiet for a while as the remaining gas settles and cools, then experience another burst when fresh gas falls in from the surrounding environment or when a merger with another galaxy brings in new fuel. This dynamic, episodic picture is messier than the smooth, continuous picture we have grown accustomed to, but it might be more accurate. It might better explain the range of galaxy properties we observe. Some galaxies caught during a burst would appear very bright and massive for their age. Others caught between bursts would appear fainter and less evolved. Depending on when we happen to observe them, we would get very different impressions of what is typical or normal. And then there are the black holes. Almost every large galaxy in the modern universe has a supermassive black hole at its center, millions, or even billions of times the mass of the Sun. Lurking in the galactic core and affecting the dynamics of everything around it. The relationship between these central black holes and their host galaxies is one of the most important and least understood topics in astrophysics. Somehow, the black hole and the galaxy grow together, their masses remaining in a tight correlation even though they are vastly different in size and the black hole contains only a tiny fraction of the galaxy's total mass. Webb has found evidence of massive black holes in the early universe as well, black holes that appear to be growing rapidly, accreting matter at tremendous rates and shining brightly as quasars, those brilliant beacons powered by matter falling into a black hole. Some of these black holes appear to be unexpectedly large for the age of the universe, just like the galaxies themselves. How do you grow a billion solar mass black hole in just a few 100 million years? There are mechanisms, ways it could happen if the conditions are right, if the black hole can continuously accrete matter at high rates, if it started from a massive seed left over from the collapse of one of those hypothetical first giant stars. But again, the timing is tight. The universe does not seem to be giving these objects enough time to grow to the sizes we observe. The presence of these massive black holes so early on raises questions about the causal relationship between black holes and galaxies. Do the black holes form first and then attract the gas that forms the galaxy? Or does the galaxy form first and then the black hole grows at its center? Or do they grow together simultaneously, feeding on the same reservoir of gas, their evolution intimately linked from the very beginning? Webb's observations are providing clues, showing us that the relationship is already established at the earliest times we can observe, suggesting that whatever process links black holes and galaxies was operating from the start. These black holes also have an important effect on their environment through feedback. When a black hole accretes matter, it doesn't do so quietly. The infalling matter heats up tremendously, radiates enormous amounts of energy, and drives powerful winds and jets that can blast gas out of the galaxy entirely. This feedback can shut down star formation by removing the raw material needed to make new stars. It can also heat the remaining gas, making it harder to collapse and form stars. Over time, this feedback is thought to regulate galaxy growth, preventing galaxies from forming stars indefinitely and explaining why massive galaxies in the modern universe are mostly dead, having exhausted their gas supplies long ago and no longer forming significant numbers of new stars. But in the early universe, the balance between star formation and black hole feedback must have been different. Galaxies were still growing rapidly, still forming stars prolifically. The feedback mechanisms might not have been as efficient, or perhaps the galaxies had access to such large reservoirs of gas that even powerful feedback could not keep up. This is another area where observations are ahead of theory. We see the results, the massive galaxies and the massive black holes coexisting in the early universe, but we are still working to understand the physical processes in detail, to build models that can reproduce what we observe. Stepping back from the specifics, from the individual galaxies and black holes and star formation rates, what are these observations really telling us? What is the deeper message here? Perhaps it is this: the universe was more capable, more resourceful, more efficient at organizing itself than we gave it credit for. We have been, in some sense, too conservative in our expectations. We assume that complexity takes time, that structure emerges slowly through the patient work of gravity and thermodynamics. And while this is true in many cases, it may not be the whole truth. Under certain conditions, under the unique circumstances of the early universe, complexity can emerge rapidly, explosively, in ways that our earthbound intuitions do not anticipate. Think about it from another angle. We live in a universe that is nearly 14 billion years old. A universe that has had vast stretches of time to evolve and develop structure. From our vantage point, deep in the history of the cosmos, we look back and see a progression from simple to complex, and we naturally assume that this progression was gradual, that each step required the one before it, that there is a strict ordering to how things must unfold. But what if this is partly an illusion of perspective? What if the early universe, newly emerged from the Big Bang, still hot and dense and far from equilibrium, was capable of things that the older, cooler, more spread-out universe we inhabit cannot do? In the early universe, everything was closer together. The density of matter was higher. The temperature was higher. The rate of physical processes was faster. A galaxy forming in that environment had access to vast reservoirs of gas all around it, gas that was still falling together under gravity, gas that had not yet been heated and dispersed by feedback from previous generations of stars because there were no previous generations yet. Perhaps, under those conditions, galaxy formation could proceed much more rapidly than it does today. Perhaps what seems impossible from our perspective was actually quite natural in that very different environment. There is an analogy here to biological evolution. When life first emerged on Earth, when the oceans were full of organic molecules and chemical energy and there were no predators, no competitors, evolution proceeded rapidly, exploring many different forms and strategies. The Cambrian explosion, that period about 540 million years ago when most major animal groups first appeared in the fossil record, represents a time when evolution accelerated, diversified, filled ecological niches at an astonishing rate. Only later, when the easy niches were filled and competition became fierce, did the pace slow down. Perhaps the early universe experienced its own Cambrian explosion, a period when galaxy formation was rapid and diverse because the conditions allowed it, before settling into the slower, more incremental evolution we observe in later epochs. But analogies only take us so far. The universe is not alive. It does not evolve through natural selection. The processes that govern galaxy formation are physical, deterministic, governed by equations we can write down. And yet there is something almost organic about the way galaxies grow, the way they feed on their surroundings, compete for resources, respond to their environment. Galaxies exist at the intersection of many forces: gravity pulling inward, pressure pushing outward, rotation providing stability, feedback regulating growth. They are complex systems, and complex systems often exhibit emergent behaviors, properties that arise from the interaction of many parts but cannot be predicted simply by understanding each part in isolation. Perhaps this is what we are really struggling with. Our models of galaxy formation, sophisticated as they are, may still be too reductionist, too focused on individual processes without fully capturing the emergent complexity that arises when all these processes interact in a dynamic, evolving universe. We can simulate gravity. We can simulate gas dynamics. We can simulate star formation and feedback. But putting it all together, capturing the full richness of how galaxies actually form and evolve, this remains one of the grand challenges of computational astrophysics. And now Webb has shown us that our simulations, our best efforts to model the universe, are missing something important. This is not a failure. This is an opportunity. Science advances not when observations confirm our theories, but when they challenge them, when they force us to think harder, dig deeper, question our assumptions. The anomalies, the contradictions, the things that don't fit, these are the signposts pointing toward new understanding. Every major breakthrough in physics has come from taking seriously something that didn't make sense, some observation that contradicted accepted theory, and following that thread until it unraveled the old picture and revealed a new one. Consider the history of cosmology itself. At the beginning of the 20th century, we believed the universe was static, eternal, unchanging. Einstein himself believed this so strongly that he added a term to his equations, the cosmological constant, specifically to keep the universe from collapsing under its own gravity. Then Edwin Hubble made his observations showing that distant galaxies are moving away from us, that the universe is expanding. This observation contradicted the static universe model. It didn't make sense according to the prevailing view. But it was true. And accepting it, following where it led, gave us the Big Bang theory, the expansion of space, the entire modern cosmological framework. Later, in the 1960s and 70s, observations of galaxy rotation curves showed that stars at the edges of galaxies were moving too fast. According to the gravity of the visible matter, these stars should be flung out into space. They should not be able to stay in orbit. This didn't make sense according to our understanding of gravity and mass. But it was true. And accepting it, following where it led, gave us dark matter, the understanding that most of the mass in the universe is invisible, that we had been seeing only a small fraction of what is really there. In the 1990s, observations of distant supernovae showed that the expansion of the universe is not slowing down as expected but accelerating. This didn't make sense according to any theory of gravity and matter. But it was true. And accepting it, following where it led, gave us dark energy, the understanding that something is pushing the universe apart, that the vacuum of space itself has energy, that our picture of the cosmos was still incomplete. Now Webb is presenting us with another set of observations that don't make sense according to our current models. Galaxies that are too large, too mature, too early. Black holes that are too massive. Star formation that is too efficient. We are at another one of those moments where the universe is telling us we don't understand it as well as we thought. Where will this lead? What will we discover when we follow this thread? What new physics, what new understanding, what new revelation about the nature of reality awaits us? It is important to emphasize that we do not yet know the answer. We are in the middle of this story, not at the end. The data is still coming in. Astronomers are still analyzing the images, measuring the spectra, refining the observations. Theorists are still running simulations, adjusting parameters, testing new ideas. There are heated debates at conferences, papers being published with contradictory interpretations, claims and counterclaims about what the data really means. This is science in action, messy and uncertain and exciting and human. Some researchers argue that the problem is less severe than it appears, that when you carefully account for all the uncertainties in measuring galaxy masses and ages, the tension with theory diminishes. Perhaps these galaxies are not quite as massive as they first seemed. Perhaps they are slightly older than we calculated. Perhaps the brightness we see is enhanced by transient phenomena, brief bursts of star formation or active black holes that make the galaxies appear more evolved than they really are. Maybe our existing models can accommodate these observations with relatively minor adjustments. Other researchers argue that the problem is real and significant, that no amount of tweaking the observations or adjusting the assumptions can make these galaxies fit into the standard picture. They point to the fact that multiple independent observations all point in the same direction, that the evidence is accumulating rather than dissolving under scrutiny. They argue that we need new physics, new models, perhaps even new understanding of how galaxies form and evolve. The truth, as it often does, likely lies somewhere in between. Some of the apparent contradictions will probably resolve as we better understand the observations and correct for various effects. But some will remain, genuine challenges that require us to revise our theories. This is not a binary situation where either everything we know is wrong or everything is fine. Reality is more nuanced. We will probably find that our basic framework is sound but incomplete, that we were missing important pieces that once added will make the whole picture clearer. One promising avenue of investigation involves looking not just at the galaxies themselves but at the gas between the galaxies, the intergalactic medium. In the early universe, most of the normal matter in the universe was not in galaxies at all but in this diffuse gas-filling space. Understanding how gas flowed from the intergalactic medium into galaxies, how it cooled and condensed and became available for star formation, this is crucial to understanding galaxy growth. Webb and other telescopes can probe this gas indirectly by observing how it absorbs light from background sources. The patterns of absorption tell us about the temperature, density, and chemical composition of the gas at different epochs. Early results suggest that gas in the early universe might have been able to cool more efficiently than we thought, perhaps because of the presence of certain molecules or because of processes we haven't fully accounted for. If gas can cool quickly, it can collapse quickly, and stars can form quickly. This might help explain the rapid growth of early galaxies. It's a piece of the puzzle that we are only beginning to explore in detail. Another piece involves better understanding the initial conditions, the seeds from which all structure grew. The cosmic microwave background radiation, the afterglow of the Big Bang, shows us the tiny variations in density that existed when the universe was only 380,000 years old. These variations are extremely small, only 1 part in 100,000, but they are the seeds that gravity amplified over time to create galaxies and clusters. We have measured these variations exquisitely well, and they match our theoretical predictions beautifully. But between the epoch of the cosmic microwave background and the epoch where we see the first galaxies with Webb, there is a gap of over 100 million years, a cosmic dark age when the universe was filled with neutral hydrogen that absorbs most light. We cannot directly observe what was happening during this period, but it is crucial because this is when the first structures were forming, when gravity was pulling matter together into the first stars and galaxies. Theorists are working hard to simulate this dark age, to model how the tiny seeds from the cosmic microwave background grew into the structures we see later. But simulations have limitations. They require enormous computational resources, and even the largest simulations cannot capture every relevant physical process at every relevant scale. There are always approximations, shortcuts, subgrid models that try to capture the average effects of processes that are too small or too fast to simulate directly. Perhaps some of these approximations are not as good as we thought. Perhaps the real universe, with all its complexity and randomness and nonlinear interactions, behaves differently than our simulated universes. This is where advances in computational power and technique will be crucial. As computers become faster and algorithms become more sophisticated, we can run more detailed simulations that include more physics, resolve smaller scales, follow the evolution for longer. We can create synthetic universes in our computers and see how they evolve under different assumptions, then compare them to the real universe observed by Webb. This back and forth between observation and simulation, each informing the other, is how we will ultimately solve these puzzles. But there is also a more philosophical dimension to consider. What does it mean that the universe surprises us? What does it mean that reality does not conform to our expectations? On one level, it is simply a reminder of human fallibility, of the limits of our knowledge and imagination. We are small creatures on a small planet trying to understand a cosmos of almost incomprehensible vastness and complexity. We do the best we can with the tools and minds we have, but we should not be surprised when we discover that reality is stranger, richer, more intricate than we imagined. On another level, it is something more profound. The universe is not obligated to make sense to us. It does not exist for our convenience or our understanding. It simply is, following its own laws, unfolding according to its own nature, indifferent to whether we comprehend it or not. That we can understand any of it, that we can peer back across billions of light years and see the infant cosmos, that we can write equations that describe how gravity shapes space and time, that we can predict with extraordinary precision the abundances of elements or the temperature of the cosmic background radiation, this is almost miraculous. We should be astonished that the universe is comprehensible at all. And yet it is. Despite its complexity, despite the challenges and mysteries, we do understand much about how the cosmos works. The fact that we are surprised by Webb's observations is itself a testament to how much we have learned. We have built models sophisticated enough that we can make predictions, and we have built instruments powerful enough to test those predictions. When the observations don't match the predictions, that is not failure. That is science working exactly as it should, providing the feedback that allows us to refine our understanding, to move closer to truth. There is something deeply human about this enterprise, this quest to understand where we came from, how the universe came to be, what our place is in the grand scheme of things. These are ancient questions, asked by every culture, every civilization, every person who has ever looked up at the night sky and wondered. For most of human history, we could only speculate, weaving myths and stories to explain the cosmos. Only in the last century have we had the tools to actually answer these questions, to gather evidence, to test our ideas against reality. And now, with James Webb, we are answering them with unprecedented detail and precision. The images themselves are breathtaking. When the first deep field images from Webb were released, showing thousands of galaxies scattered across a tiny patch of sky, each one a complete universe of billions of stars, the world stopped and stared. Here was the cosmos in all its glory, vast and ancient and beautiful beyond words. Every galaxy in those images has a history, a story of formation and evolution spanning billions of years. Every galaxy contains worlds, perhaps some with life, with consciousness, with beings asking the same questions we ask. The sheer scale of it, the abundance and diversity of it, is overwhelming. But beyond the immediate visual impact, beyond the aesthetic beauty, these images are documents, records, data. Each galaxy's light tells a story. The color tells us about the types of stars it contains. The brightness tells us about its mass and activity. The spectrum tells us about its chemical composition and motion. The shape tells us about its dynamical state, whether it is calm and settled or disturbed and interacting. All of this information, encoded in light that has traveled across the universe for billions of years, is now being decoded, analyzed, turned into understanding. And the work is just beginning. Webb has been operating for only a short time relative to its expected mission lifetime. There are years of observations ahead, targets being selected, proposals being written, data being collected. Each new observation has the potential to reveal something unexpected, to challenge our assumptions, to deepen the mystery or help solve it. This is what makes this moment in time so extraordinary. We are living through a revolution in our understanding of the universe. Future generations will look back at this era as a turning point, the time when we finally saw the infant cosmos clearly, when we confronted the limitations of our theories, when we took the next step toward a more complete picture of reality. What will that picture look like? What will we ultimately conclude about these early massive galaxies, about the timeline of cosmic evolution, about the processes that shape the universe we inhabit? It is too soon to say with certainty. But we can speculate, cautiously, about the directions the science might go. Perhaps we will find that dark matter has properties we didn't know about, that it can interact in ways that speed up structure formation. Perhaps we will find that the first stars were even more massive and luminous than we thought, that they could enrich the universe with heavy elements more quickly. Perhaps we will find that galaxy mergers in the early universe were more common and more efficient than we modeled, allowing large galaxies to assemble rapidly through collisions and combinations. Or perhaps the solution will be something we haven't thought of yet, some mechanism or process that hasn't been proposed, some insight that will seem obvious in retrospect but eludes us now. This is the nature of discovery. You cannot know in advance what you will find. You can only keep looking, keep questioning, keep testing your ideas against observation, and trust that eventually clarity will emerge from confusion. What is clear already is that the early universe was a more dynamic, more active, more complex place than we envisioned. The first billion years of cosmic history were not a slow, quiet period of gradual assembly but a dramatic, turbulent epoch of rapid transformation. The universe changed more quickly than we thought possible, went from nearly featureless uniformity to rich structure in what cosmologically speaking is the blink of an eye. This realization changes how we think about cosmic history, compressing the timeline, accelerating the drama, making the story of the universe more intense and more astonishing. It also has implications for the broader question of our place in the universe, the possibility of life elsewhere. If galaxies formed quickly, if stars lit up the cosmos earlier than we thought, if heavy elements necessary for life were synthesized more rapidly, then the conditions for life could have existed sooner. Perhaps there are planets in the early universe, planets around stars in these young galaxies, planets that have had billions of years to develop complex ecosystems, even civilizations. Perhaps we are not among the first intelligent species to emerge in the cosmos but are actually latecomers to a universe that has been inhabited for far longer than we realized. This is, of course, speculation. We have no direct evidence of life beyond Earth. We have not detected any signals, any signs, any definitive proof that we are not alone. But the discovery that the universe organized itself so quickly, that complexity emerged so early, makes the possibility of widespread life seem more plausible. If nature can create massive galaxies in just a few 100 million years, perhaps it can create life just as readily, given the right conditions and enough time. But let us not get too far ahead of ourselves. The question of life in the universe, profound as it is separate from the immediate puzzle of these early galaxies. We must focus on what we can observe, what we can measure, what we can test. And right now, what we can test are models of galaxy formation, theories of structure formation, predictions about when and how galaxies should appear in the early universe. This is the immediate challenge before us, the problem that Webb has brought into sharp focus. And it is a worthy challenge, one that will occupy astronomers and physicists for years to come, one that will drive theoretical development and observational campaigns, one that will push the boundaries of our understanding. This is what science is supposed to do, to confront us with mysteries that demand explanation, to show us where our knowledge ends and our ignorance begins, to motivate us to do better, to think harder, to look more carefully. In this sense, the crisis that Webb has created is not a crisis at all. It is an opportunity. It is a gift. We are being shown that the universe still has secrets to reveal, that we have not figured everything out, that there is still so much to discover. This is exciting. This is why people dedicate their lives to studying the cosmos. Not because we have all the answers, but because we don't, because there are still questions to ask and mysteries to solve and wonders to uncover. As we continue to analyze Webb's observations, as we refine our measurements and improve our models, as we gather more data and test more ideas, we will gradually piece together a more accurate picture of the early universe. It will take time. There will be false starts and dead ends and debates that go on for years. But eventually, clarity will emerge. We will understand why galaxies formed so quickly, how they managed to assemble such mass in such a short time, what processes were at work in that ancient epoch. And when we do, when we finally solve this puzzle, we will have learned something profound about the universe, something that changes our perspective and enriches our understanding. But even then, even when we think we have solved this mystery, the universe will likely surprise us again. There will be new observations, new anomalies, new questions. This is the pattern of scientific progress. Each answer leads to new questions. Each mystery solved reveals deeper mysteries beneath. We climb one mountain only to see a range of higher peaks beyond. And this is good. This is how it should be. A universe that held no more mysteries would be a boring place, a place where there was nothing left to learn, no reason to keep exploring. Better to live in a universe that constantly challenges us, that rewards our curiosity with glimpses of profound truths but never gives up all its secrets at once. The galaxies that Webb has revealed to us, those impossible bright structures shining at the edge of time, they are messengers from the deep past. They are telling us something about the universe we live in, about its history and its nature. They are reminding us that reality is not bound by our expectations, that the cosmos is under no obligation to behave the way we think it should. They are inviting us to think more deeply, to question more carefully, to explore more thoroughly. They are challenging us to be better scientists, better thinkers, better seekers of truth. And in rising to that challenge, in doing the hard work of reconciling observation with theory, of building new models and testing new ideas, of pushing the limits of our technology and our understanding, we are doing something fundamentally human. We are trying to make sense of the world, to find order in chaos, to understand where we came from and how we got here. This drive, this curiosity, this need to know, it is one of the defining characteristics of our species. It is what led us out of caves and across continents, what drove us to build civilizations and develop science, what pushes us now to explore the cosmos with ever more powerful instruments. James Webb is just the latest chapter in this long story, this ongoing human quest to understand the universe. It will not be the last. Already, astronomers are planning the next generation of telescopes, instruments even larger and more sensitive than Webb, capable of seeing even further back in time, even deeper into space. There will be ground-based telescopes with mirrors tens of meters across, capable of gathering enormous amounts of light and resolving fine details. There will be space-based telescopes optimized for different wavelengths, different science goals, different questions. Each will contribute to our growing understanding, each will reveal new aspects of the cosmos, each will likely surprise us in ways we cannot anticipate. But for now, Webb is our window to the early universe. It is showing us things we have never seen before, challenging ideas we thought were settled, opening questions we thought were answered. And in doing so, it is reminding us of a fundamental truth about the universe and about science itself: we never stop learning. We never reach a point where we know everything. There is always more to discover, always deeper layers of reality to explore, always new mysteries waiting just beyond the edge of what we understand. The massive galaxies at the cosmic dawn, those structures that shouldn't exist according to our models, they are not problems to be solved and forgotten. They are invitations to think differently, to imagine possibilities we had not considered, to look at the universe with fresh eyes. They are telling us that the cosmos is more creative, more resourceful, more remarkable than we gave it credit for. They are showing us that in the extreme conditions of the early universe, under circumstances far removed from anything we experience in our local corner of space and time, nature found ways to organize matter and energy that we are only beginning to comprehend. This is both humbling and thrilling. Humbling because it reveals how much we still don't know, how tentative even our best theories are, how the universe can always surprise us. Thrilling because it means there is still so much to discover, so many questions to explore, so many revelations waiting for us if we just keep looking, keep questioning, keep pushing the boundaries of what is possible. And so we will keep looking. Astronomers will keep analyzing Webb's data, finding new galaxies, measuring new properties, testing new ideas. Theorists will keep running simulations, building models, trying to understand what physical processes could produce what we observe. Engineers will keep designing new instruments, new telescopes, new ways to probe the universe with ever greater sensitivity and precision. This work will continue for years, for decades, for as long as humans are curious about the cosmos. Because ultimately, this is not just about galaxies or cosmology or abstract questions of physics. This is about us, about who we are and where we came from. The atoms in our bodies were forged in stars, scattered through space in supernova explosions, incorporated into planets, assembled into living organisms. We are, quite literally, made of stardust. The history of the universe is our history. The story of how galaxies formed and evolved is the story of how the conditions arose that made our existence possible. Understanding the cosmos is, in a deep sense, understanding ourselves. When we look at those early galaxies through Webb's golden eye, when we see light that has traveled for over 13 billion years to reach us, we are looking at our origins. Not our immediate origins, not the formation of Earth or the evolution of life, but our ultimate cosmic origins, the processes that created the universe we inhabit, that built the stage on which the drama of life could eventually unfold. Those ancient galaxies are our ancestors in a very real sense. The stars within them created the elements that would eventually become part of us. The processes that shaped them are the same processes that, given billions more years of cosmic evolution, would lead to the solar system, to Earth, to life, to consciousness, to creatures capable of building telescopes and wondering about their place in the universe. So when we find that those galaxies don't behave the way we expected, when we discover that they formed too quickly or grew too large or appeared too early, we are not just encountering a technical problem in astrophysics. We are encountering a mystery about our own origins, a gap in our understanding of how the universe became capable of producing us. Solving that mystery, understanding how galaxies could form so rapidly in the early universe, brings us closer to understanding the full story of cosmic evolution, the chain of events that led from the Big Bang to the present moment, from simplicity to complexity, from uniformity to diversity, from lifeless matter to living, thinking beings asking questions about it all. This is why the anomalies matter. This is why the observations that don't fit are so important. They are telling us that our story is incomplete, that we are missing crucial chapters, that the narrative we have constructed is not quite right. And rather than being frustrating or discouraging, this should energize us. It means there is more story to uncover, more history to reconstruct, more understanding to gain. The universe has been patient with us. It has been here, doing its thing, following its laws, evolving and changing, for nearly 14 billion years. We, Johnny-come-latelys that we are, have been studying it scientifically for barely a few centuries. We have had telescopes capable of seeing into the deep universe for mere decades. James Webb itself has been operating for only a tiny fraction of a percent of cosmic history. And yet, in this brief moment, we have learned so much. We have measured the age of the universe. We have mapped its large-scale structure. We have traced its expansion history. We have identified its major components, even if we don't yet understand what they all are. We have reconstructed the timeline of cosmic evolution from the Big Bang to the present with remarkable detail and accuracy. But there are still gaps. There are still uncertainties. There are still mysteries. And Webb is revealing some of those mysteries to us now, showing us where our understanding breaks down, where our models fail, where reality deviates from our expectations. This is not a failure of science but a triumph of it. We have built instruments sensitive enough to detect these deviations. We have developed theories precise enough that we can identify when observations don't match predictions. We have created a scientific culture that values anomalies and contradictions, that sees them not as problems to be hidden or ignored but as opportunities to learn something new. The next few years will be crucial. As more data comes in from Webb and other telescopes, as more galaxies are discovered and characterized, as spectroscopy reveals their chemical compositions and dynamics, we will build up a statistical picture of what the early universe really looked like. We will move beyond individual striking examples to population studies, understanding not just that some galaxies are surprisingly massive but how common such galaxies are, what fraction of all galaxies at that epoch have these properties, how they are distributed across space and time. This statistical approach will help us constrain theories. A good theory doesn't just need to explain individual observations but needs to reproduce the overall properties of the galaxy population. It needs to predict not just that massive galaxies exist but how many there should be, how their masses should be distributed, how their properties should correlate with their environment and their age. This is a much more stringent test than simply finding one or two examples of unusual galaxies. And theories will evolve. Theorists are already working on modifications to the standard galaxy formation models, incorporating new physics, adjusting parameters, exploring different scenarios. Some of these modified models will successfully reproduce the observations. Others will fail. Through this process of proposing ideas, testing them against data, and refining or discarding them based on how well they work, we will gradually converge on a better understanding. This is the scientific method in action. It is not always elegant or straightforward. It involves false starts and controversies and debates. It can be frustratingly slow at times, as competing ideas are tested and retested, as evidence accumulates gradually, as consensus slowly builds. But it works. Over time, through this iterative process, we get closer to the truth. Our models become more accurate. Our understanding becomes deeper. Our picture of reality becomes clearer. And there will be breakthroughs. There always are. Someone will have an insight, make a connection, see a pattern that others missed. Someone will propose a new mechanism or identify a critical process that had been overlooked. And suddenly, pieces that seemed disconnected will fit together. Observations that seemed contradictory will make sense. The puzzle will resolve, at least partially, and we will have a new framework for understanding the early universe. When that happens, and it will happen, we will look back at this period of confusion and uncertainty as a productive time, a necessary phase in the growth of knowledge. We will see that the anomalies Webb revealed were not problems but clues, signposts pointing toward deeper truth. We will understand that the discomfort we felt when observations contradicted theory was the discomfort of growth, of expanding our understanding beyond its previous limits. But even as we solve these immediate mysteries, we should not expect that all questions will be answered. The universe is deep. Reality has layers. Each time we penetrate one layer, we find another beneath it. This is the nature of scientific inquiry. We never reach a final theory of everything, never arrive at complete and total understanding. There is always more complexity, always deeper structure, always new phenomena emerging at scales we haven't yet explored or energies we haven't yet accessed or regimes we haven't yet studied. And this is fine. This is, in fact, wonderful. Because it means the adventure never ends. There is always more to discover, always new questions to ask, always new frontiers to explore. Each generation of scientists gets to participate in this grand project of understanding the universe, gets to contribute their piece to the growing edifice of knowledge, gets to experience the thrill of discovery and the satisfaction of solving mysteries that have puzzled humanity for ages. We are living in that moment now. We are part of the generation that got to see, for the first time, clear and detailed images of galaxies at the cosmic dawn. We are the ones grappling with the implications of those observations, working to reconcile them with theory, pushing the boundaries of understanding. Future historians of science will study this period, will read the papers being written now, will trace how our understanding evolved as we confronted these challenges. And they will do so from the perspective of whatever new understanding emerges, whatever synthesis we eventually achieve, whatever deeper picture of cosmic evolution we construct. But they will also face their own mysteries, their own anomalies, their own observations that don't quite fit. Because the universe will continue to surprise us, no matter how much we learn, no matter how sophisticated our theories become. There is always another layer of reality to explore, always another question to ask, always another mystery waiting to be uncovered. And so the work continues. The observations continue. The analysis continues. The theorizing continues. The debates continue. This is science as a living, breathing, evolving enterprise, not a collection of fixed facts but an ongoing process of inquiry and discovery. And we, all of us who wonder about the cosmos, who ask questions about where we came from and how the universe works, we are all part of this enterprise. We are all participants in this grand human project of understanding reality. The massive galaxies in the early universe, shining impossibly bright across billions of light years, are calling to us. They are asking us to think more deeply, to question more thoroughly, to imagine more boldly. They are reminding us that the universe is not a simple place, not a place that reveals its secrets easily, not a place that confirms our expectations without challenge. They are telling us that reality is rich and complex and strange and beautiful and full of surprises. And we are answering that call. With telescopes like Webb, with simulations running on powerful computers, with theories that probe the fundamental nature of matter and energy and space and time, we are reaching out across the vast gulf of cosmic history, touching the infant universe, trying to understand how it grew and evolved into the cosmos we inhabit today. This is one of the most ambitious things humans have ever attempted, and we are succeeding. Not perfectly, not completely, not without struggle and setbacks and moments of confusion. But we are succeeding. We are learning. We are growing in understanding. And that, ultimately, is what this is all about. Not the specific details of galaxy formation models or star formation rates or black hole masses, important as those are to specialists in the field. But the larger project of human understanding, the quest to comprehend our place in the cosmos, the drive to know and understand and make sense of the universe we find ourselves in. This is what motivates the scientists who dedicate their careers to studying distant galaxies. This is what justifies the billions of dollars and years of effort required to build and launch telescopes like Webb. This is what makes the discoveries meaningful, not just to specialists but to everyone, to all of humanity. Because these are our origins being revealed. This is our story being uncovered. These ancient galaxies, however much they may confuse and surprise us, are part of the long chain of cosmic evolution that led to us. Understanding them is understanding ourselves at the deepest level. It is connecting our brief lives to the immense sweep of cosmic history. It is realizing that we are not separate from the universe but intimately connected to it, products of its processes, participants in its ongoing evolution. So let the galaxies be surprising. Let them challenge our theories and force us to think harder. Let them remind us that the universe is more remarkable than we imagined, more creative in its solutions, more capable of producing complexity and structure and beauty. Let them inspire us to keep exploring, keep questioning, keep pushing the boundaries of what is possible. Because in doing so, we are not just learning about distant objects billions of light years away. We are learning about ourselves, about where we came from, about the profound connection between the smallest particles and the largest structures, between the briefest moments and the vast expanse of cosmic time, between the material and the meaningful. The James Webb Space Telescope has shown us the universe as it was over 13 billion years ago. It has revealed galaxies that shouldn't exist, that defy our expectations, that challenge our understanding. But perhaps the real revelation is not about those galaxies at all. Perhaps it is about us, about our capacity to build instruments that can see across such vast distances, about our ability to ask deep questions about the cosmos, about our willingness to confront mysteries that challenge our most carefully constructed theories. Perhaps the real revelation is that we are a species capable of looking back to the dawn of time and trying to understand what we see, even when what we see doesn't make sense, even when it forces us to question everything we thought we knew. This capacity for wonder, for curiosity, for relentless questioning in the face of mystery, this is what makes us human. This is what drives science forward. This is what will eventually solve the puzzle of the early massive galaxies and whatever puzzles come after. Not certainty, not dogmatic adherence to existing theories, but openness to surprise, willingness to be wrong, commitment to following the evidence wherever it leads. The universe looked back 13.5 billion years reveals itself to be stranger than we imagined. And that is exactly as it should be. That is the universe teaching us, once again, that our imagination, vast as it is, cannot encompass all of reality. That there are truths we have not yet dreamed of, phenomena we have not yet witnessed, processes we have not yet understood. And that is not a limitation but an invitation. An invitation to keep looking, keep learning, keep growing in understanding. An invitation to participate in the grand ongoing project of human knowledge, the collective effort to understand the cosmos that gave birth to us. The telescope continues to observe. The data continues to accumulate. The mystery continues to deepen even as our understanding grows. And somewhere, in all of this, in the interplay between observation and theory, between expectation and reality, between what we know and what we are learning, lies the truth about how the universe evolved, how galaxies formed, how we came to be. We may not have that truth yet. We may not have it for years. But we are getting closer with every observation, every measurement, every new idea tested against the data. And when we do finally understand, when the pieces fall into place and the picture becomes clear, when we can confidently explain how massive galaxies could form so quickly in the early universe, it will be because we followed where Webb led us. Because we took seriously the observations that didn't fit. Because we were willing to question our assumptions and revise our theories and think in new ways about old problems. And we will be richer for it, not just in knowledge but in perspective, in our understanding of what the universe is capable of, in our appreciation for the profound processes that shaped the cosmos and made our existence possible. Until then, we live with the mystery. We hold in our minds the tension between what we see and what we thought we knew. We work to resolve that tension, to find the synthesis that makes sense of both observation and theory. And we marvel at the fact that we can do this at all, that we have reached a point in our development as a species where we can build instruments capable of seeing to the edge of time itself, where we can ask questions about the first galaxies and actually gather data to answer them, where we can participate directly in uncovering the history of the universe. The cosmos is vast. Our lives are brief. But in this brief moment, with telescopes like Webb, we can touch the infinite. We can see across billions of years. We can witness the birth of galaxies, the forging of elements, the emergence of structure from chaos. We can ask the deepest questions about existence itself and begin, just begin, to find answers. And in doing so, we transcend our limitations, connect ourselves to something far larger and longer lasting than our individual lives, participate in a quest for understanding that spans generations and cultures and centuries. This is what the impossible galaxies are teaching us. Not just facts about star formation and gravitational collapse, important as those are. But something about the human capacity to wonder, to question, to seek understanding even when the questions are hard and the answers are elusive. They are reminding us that we are creatures capable of building golden mirrors and launching them into space to catch photons that have been traveling since the dawn of time. Capable of decoding those photons to reconstruct the history of the universe. Capable of being surprised by what we find and having the courage to admit when our theories need revision. This is our moment in cosmic history. This is our contribution to the long human project of understanding reality. And whatever we ultimately learn about those early massive galaxies, whatever resolution we find to the mysteries Webb has revealed, the real story is the journey itself. The reaching out across the cosmos. The asking of questions so profound that they touch the origins of existence. The patient gathering of data. The careful construction of theories. The willingness to be wrong. The persistence in seeking truth despite setbacks and uncertainties. This is what it means to be human in the age of James Webb. To stand on this small planet and look back across 13 billion years. To see things that shouldn't exist and ask why. To refuse to accept easy answers. To demand that our theories account for what we actually observe, not just for what we expect to observe. To participate, each in our small way, in the grand ongoing conversation about the nature of reality, the history of the cosmos, the origins of everything we know. The galaxies are still there, shining in the deep past, waiting to reveal their secrets. The data is still streaming down from the telescope. The scientists are still analyzing, theorizing, debating, discovering. The mystery endures, deep and rich and fascinating. And we, all of us who wonder about these things, we are all part of this moment, this extraordinary time when humanity is seeing the infant universe clearly for the first time and grappling with what it means. What will we ultimately learn? How will this story end? We cannot know yet. The answer is still being written, still emerging from the data, still taking shape in the minds of those who study these phenomena. But we can be certain of this: whatever we learn will change us. It will change how we see the universe. It will change our place within it. It will change our understanding of how things came to be. And in changing our understanding, it will change us, because we are creatures shaped by our knowledge, defined in part by what we know about the world and our place in it. The James Webb Space Telescope looked back 13.5 billion years. What it found was not just galaxies but questions, deep and profound questions about how the universe works, how it evolved, how it managed to create the complexity and beauty we observe. These questions are still being answered. The work continues. The exploration goes on. And somewhere in that ongoing process, in the patient accumulation of observations and the careful refinement of theories, lies the future of our understanding, the next chapter in the human quest to comprehend the cosmos. This is where we are. This is what we are doing. This is who we are as a species, curious, persistent, capable of reaching across the universe with instruments and imagination, capable of being humbled by what we find and inspired to search for deeper understanding. The massive galaxies of the early universe stand as monuments to what we have yet to learn, reminders that the cosmos is full of surprises, that reality exceeds our expectations, that there is always more to discover for those brave enough to look. And so we look. And so we wonder. And so we work to understand. Because this is what we do. This is what we are. Creatures of curiosity standing on the edge of infinity, asking questions about everything, refusing to be satisfied with ignorance, insisting on understanding even when understanding is difficult and the questions are hard and the answers challenge everything we thought we knew. This is the human adventure. This is our story. And the universe, vast and ancient and full of impossible wonders, is waiting to see what we will discover next. Retry Webb, James Webb. Webb. The telescope does not merely see distant objects. It sees time itself, frozen in light. Every photon that strikes its golden mirror has been traveling through expanding space for eons, carrying information not just about where it came from but when. And here is something we have not yet fully grasped about what Webb reveals: these galaxies are not simply old. They are impossibly organized, displaying symmetries and structures that imply mechanisms we have not yet identified. Look closely at the spectra, at the precise measurements of chemical abundances in these ancient systems. Oxygen appears in quantities that demand explanation. Nitrogen exists where it should not. Carbon enriches the gas at levels requiring stellar processing that, by conventional timelines, has not had opportunity to occur. Each element tells a story of nuclear fusion, of stars burning through their fuel, of supernovae scattering their manufactured atoms into space. But the chapters of this story appear out of order, pages shuffled, the narrative timeline compressed beyond recognition. Some galaxies Webb observes show dust. Not trace amounts, not the faint suggestions we expected, but substantial quantities of cosmic dust, those microscopic grains of silicates and carbonaceous material that form in the cooling ejecta of dying stars. Dust is complicated. It requires not just heavy elements but specific conditions for those elements to condense into solid particles. It requires time for stellar winds and supernova shocks to process gas into these tiny grains. Finding abundant dust in galaxies barely 300 million years after the Big Bang is like discovering sophisticated pottery at a campsite dated to the very dawn of human habitation. The craftsmanship exceeds what the timeline permits. The morphologies perplex us equally. We see disk structures, spiral hints, ordered rotation patterns suggesting that these galaxies have already undergone dynamical relaxation. That random motions have settled into coherent rotation, that chaos has organized itself into form. Simulations tell us this process requires time, requires the galaxy to experience enough orbital periods for gravitational interactions to smooth out irregularities, for the system to find equilibrium. Yet here they are, already in equilibrium, already displaying the hallmarks of maturity when they should still be violent and disordered. Perhaps we have been asking the wrong questions entirely. We assumed galaxy formation was a process of accumulation, of small things gradually combining into larger things through mergers and accretion. This bottom-up paradigm felt natural, intuitive, consistent with how we understood structure formation from cosmic microwave background seeds. But what if, under certain extreme conditions, galaxies can form top-down? What if there are ways for large gas clouds to collapse directly, fragmenting internally to form stars while maintaining overall structure? What if the distinction between star cluster and galaxy, so clear in the modern universe, was blurred in the early cosmos? There are theoretical frameworks that permit such scenarios. If cooling is efficient enough, if turbulence in the primordial gas follows specific patterns, if dark matter halos assemble in particular ways, you can imagine modes of galaxy formation that bypass the slow hierarchical assembly we observe locally. These frameworks exist at the edges of mainstream thought, proposed but not widely accepted, mathematical possibilities waiting for observational vindication. Webb may be providing that vindication, forcing us to take seriously ideas that seemed too exotic, too removed from conventional wisdom to warrant serious attention. Consider what happens when you abandon the assumption of gradual growth. Suddenly, the timeline constraints relax. If a galaxy can assemble its mass in a single rapid collapse event rather than through multiple merger generations, you compress the formation timescale dramatically. If star formation is not continuous but comes in massive coordinated bursts, you can produce large stellar populations quickly. If feedback from supernovae and black holes is less efficient at escaping the deep gravitational wells of rapidly forming systems, the gas remains available for subsequent star formation rather than being expelled into the intergalactic medium. These are not minor adjustments to existing models. These are fundamental reconceptualizations of how galaxies come into being. And they carry profound implications that ripple through our entire cosmological framework. If early structure formation proceeded differently than we thought, then our interpretation of the cosmic microwave background may require revision. Those tiny temperature fluctuations we measure so precisely, those statistical properties we fit to cosmological parameters, they are the initial conditions for structure formation. If structure forms differently than our models assume, then the connection between those initial conditions and the observed universe changes, and we may need to revisit conclusions we thought were firmly established. The tension with the cosmic microwave background is subtle but real. That primordial radiation shows us an extremely uniform universe, variations of only 1 part in 100,000. These variations are small enough that linear perturbation theory should apply well into the universe's early history, meaning structure grows predictably, gradually, following equations we can solve analytically. But if Webb is showing us galaxies that formed more rapidly than linear theory permits, then nonlinear effects must have become important earlier, must have amplified structure growth in ways we have not properly accounted for. This points toward deficiencies in our understanding of the transition from linear to nonlinear regime, that critical epoch when gentle ripples in the cosmic density field became pronounced peaks and valleys. Some cosmologists whisper about even more radical possibilities. What if the initial fluctuations were not quite as we understood them? What if there were rare, high-amplitude peaks in the primordial density field? Statistical outliers that seeded unusually rapid structure formation in localized regions. Such peaks could exist within the statistical framework of inflation, the theory that describes how quantum fluctuations in the early universe were stretched to cosmic scales, but they would be rare enough that they might not dominate the average properties we measure in the cosmic microwave background. Perhaps Webb is finding these rare regions, these cosmic hotspots where conditions permitted accelerated galaxy formation. Or perhaps the problem lies with dark matter itself, that invisible scaffolding upon which galaxies supposedly form. We have evidence that dark matter exists, but we know almost nothing about its particle nature. We assume it is cold, moving slowly enough to clump on all scales, forming the hierarchical structure of halos within halos that our simulations predict. But what if dark matter has unexpected properties? What if it can dissipate energy through interactions we have not identified, allowing dark matter halos to collapse more rapidly? What if there are multiple types of dark matter particles, some cold and some with different characteristics, creating a richer phenomenology than our simplified models capture? Recent theoretical work explores self-interacting dark matter, particles that can scatter off each other through forces acting only in the dark sector. Such interactions could alter the internal structure of dark matter halos, potentially making them more conducive to galaxy formation under certain conditions. Other work examines fuzzy dark matter, ultralight particles that behave quantum mechanically on galactic scales, creating interference patterns and core structures that differ from standard cold dark matter predictions. These exotic possibilities remain speculative, but Webb's observations provide new motivation to take them seriously, to work out their detailed predictions and compare them to what we observe. The supermassive black holes complicate matters further. Not only are they present in the early universe, but they appear to be growing at rates that challenge our understanding of accretion physics. There are fundamental limits to how fast a black hole can grow by swallowing matter. As material falls toward the black hole, it heats up and radiates, and that radiation pressure pushes against the infalling matter, creating a maximum accretion rate called the Eddington limit. To grow a billion solar mass black hole in a few 100 million years starting from a stellar remnant of tens of solar masses requires continuous accretion at or above this limit for the entire time period. This is possible in principle but requires perfect conditions, a constant supply of gas funneled directly toward the black hole with minimal interruption. But nature is rarely so cooperative. Feedback from the black hole itself should disrupt accretion, blowing away nearby gas and temporarily starving the black hole. The host galaxy undergoes violent processes, mergers and starbursts that stir and heat the gas, sometimes making it unavailable for accretion. Maintaining steady rapid growth through all this turbulence seems implausible. Some theorists propose that the seed black holes were not stellar mass remnants but much more massive to begin with, perhaps hundreds or thousands of solar masses, formed through exotic mechanisms like the direct collapse of massive gas clouds. Starting from larger seeds makes the growth problem more tractable, but it introduces new questions about how such massive seeds could form and how common they might be. The symbiosis between black holes and their host galaxies appears established from the earliest times. We see correlations between black hole mass and galaxy properties, suggesting they evolved together, their growth somehow coupled. But the mechanism of this coupling remains mysterious. How does a black hole containing a tiny fraction of the galaxy's mass exert such profound influence on the galaxy's evolution? The answer involves energy, vast quantities of energy released by accretion that can heat and expel gas from the entire galaxy, regulating star formation on scales millions of times larger than the black hole itself. This feedback connects the smallest scales, the event horizon of the black hole, to the largest scales, the diffuse gas throughout the galaxy, creating a system of exquisite complexity. Webb spectroscopy capabilities allow us to probe these systems in unprecedented detail. By spreading the light from a galaxy into its component wavelengths, we create a spectrum showing bright emission lines at specific wavelengths corresponding to electron transitions in various atoms. The pattern of these lines tells us what elements are present. The width of the lines tells us about motion, about how fast gas is swirling or flowing. The ratios between different lines tell us about temperature, density, ionization conditions, revealing the physical state of the gas. This spectroscopic information transforms galaxies from mere points of light into physical laboratories where we can study conditions utterly unlike anything in our local universe. The emission lines from these early galaxies show strong oxygen and carbon features, confirming the presence of processed elements. They show broad lines from rapidly moving gas, suggesting powerful outflows driven by star formation or black hole activity. They show unusual ratios that indicate the gas is being ionized by radiation harder than what typical stellar populations produce, perhaps pointing toward exotic stellar types or contributions from accreting black holes. Every spectrum is a puzzle, a collection of clues that must be assembled into a coherent picture of what physical processes are occurring in these distant systems. Some galaxies show signs of multiple kinematic components, gas moving at different velocities in different parts of the galaxy. This could indicate merger activity, two galaxies in the process of colliding and combining. Or it could reflect complex internal dynamics, rotation coupled with inflows or outflows. Disentangling these possibilities requires careful analysis, modeling the expected spectral signatures from different scenarios and comparing them to observations. The data is often ambiguous, consistent with multiple interpretations, reminding us that astronomy is fundamentally an inverse problem where we try to infer three-dimensional structure and dynamics from two-dimensional images and one-dimensional spectra. The infrared wavelengths where Webb operates are crucial for this endeavor. Because the universe is expanding, light from distant objects is redshifted, stretched to longer wavelengths. The more distant an object, the greater its redshift. For galaxies at the edge of the observable universe, even ultraviolet light emitted by hot young stars is redshifted all the way into the infrared. Hubble, operating primarily at optical and near-infrared wavelengths, could barely detect these objects. Webb, designed specifically for infrared observation, sees them clearly. This is not just a quantitative improvement but a qualitative transformation, opening a window that was previously closed. The technology enabling this observation is itself extraordinary. Webb's mirror, over 6 meters in diameter, comprises 18 hexagonal segments that must be aligned to nanometer precision, acting as a single coherent surface. This mirror is coated with gold, which reflects infrared light efficiently. The entire telescope is kept at temperatures below 50 Kelvin, cold enough that its own thermal emission does not overwhelm the faint infrared signals from distant galaxies. To achieve this temperature, Webb sits at a gravitationally stable point a million miles from Earth, protected by a tennis court-sized sunshield that blocks heat and light from the Sun, Earth, and Moon. Every aspect of the telescope's design serves the singular purpose of detecting infrared photons that have traveled across cosmic epochs to reach us. The detectors themselves are marvels of engineering, sensitive enough to register individual photons, precise enough to measure their wavelengths with high resolution. The data processing pipeline that converts raw detector counts into scientifically calibrated spectra and images involves sophisticated algorithms correcting for instrumental effects, cosmic ray hits, background light, and myriad other contaminating signals. The final products, the images and spectra that astronomers analyze, represent the culmination of decades of technological development and careful calibration, each observation the result of countless hours of work by engineers, technicians, and scientists. Yet for all this technological sophistication, for all the resources invested in building and operating Webb, the telescope cannot answer the fundamental questions on its own. It provides data, exquisite data, the best observations of the early universe ever obtained. But data is not understanding. Data must be interpreted, compared to theoretical models, placed into frameworks that give it meaning. And when the data contradicts our frameworks, when it shows us things that do not fit, we face a deeper challenge than any technological one. We must rethink our assumptions, revise our theories, construct new frameworks that accommodate what we observe while remaining consistent with everything else we know. This interplay between observation and theory is science at its most fundamental. Neither alone is sufficient. Theory without observation becomes untethered speculation. Observation without theory is mere stamp collecting, cataloging phenomena without understanding them. Together, they form a feedback loop where observations constrain theories and theories suggest new observations, each driving the other forward, each revealing inadequacies in the other, each pushing us toward more complete understanding. The current moment represents a period where observation has leaped ahead of theory. Webb has shown us things theory did not predict, has revealed a universe richer and more complex in its early history than our models anticipated. Now theory must catch up. Theorists must propose new mechanisms, new physics, new ways of understanding galaxy formation that can account for what we see. These proposals will make predictions, suggesting other observables, other tests that can confirm or refute them. Some theories will survive these tests. Others will fail. And gradually, through this process of proposal and testing, of refinement and elimination, we will converge on better understanding. But convergence takes time. Science does not proceed in sudden leaps where everything becomes clear at once. It advances incrementally, through accumulated evidence and gradual consensus building. There will be periods of confusion when multiple competing theories seem equally viable. There will be controversies where different camps advocate different interpretations of the same data. There will be premature claims of solutions that later prove inadequate. This messiness is not a flaw but a feature, the natural state of science at the frontier where knowledge is being actively created. The implications extend beyond galaxy formation itself. If we must revise our understanding of how galaxies form, that revision affects everything downstream. The history of star formation in the universe, the production of heavy elements, the evolution of the intergalactic medium, the formation of planets, even the conditions under which life might emerge, all depend on when and how galaxies assembled. Get the galaxy formation timeline wrong, and you potentially get the entire cosmic history wrong. This is why the Webb observations matter so profoundly. They are not just about galaxies but about the entire narrative of cosmic evolution. Consider the star formation history of the universe. We have believed that star formation ramped up gradually, reaching a peak several billion years after the Big Bang before declining as galaxies exhausted their gas supplies. This, cosmic star formation history, is derived from observations of galaxies at different epochs, measuring how much stellar mass is forming per unit volume of space as a function of time. If massive star-forming galaxies existed earlier than we thought, if the early universe was more active than we believed, then the star formation history must be revised. The peak may have been earlier, the rise steeper, the total amount of stellar mass formed in the first billion years much larger. This matters for chemical enrichment. Every generation of stars processes primordial hydrogen and helium into heavier elements. The more stars that have lived and died, the more enriched the universe becomes. If early star formation was more vigorous, then enrichment proceeded more rapidly, and the heavy elements necessary for planet formation, for chemistry, for life, became available sooner. This opens the possibility that habitable planets could have formed earlier than conventional timelines suggest, that life might have arisen in the universe long before it appeared on Earth, that we might be latecomers to a cosmos that has been inhabited for most of its history. The intergalactic medium, that vast expanse of gas between galaxies, has its own evolutionary story intimately connected to galaxy formation. In the very early universe, this gas was neutral, transparent to radio waves but opaque to ultraviolet light. Then the first stars and galaxies began to shine, emitting ultraviolet radiation that ionized the surrounding gas, creating bubbles of ionized plasma around each source. These bubbles grew and merged until eventually the entire universe was reionized, completing a cosmic phase transition from neutral to ionized that fundamentally changed the properties of the intergalactic medium. We believe this reionization occurred gradually over several 100 million years, but we do not know the precise timeline or which sources dominated the ionizing radiation. Webb's observations bear directly on reionization. If there are more galaxies in the early universe than we thought, and if those galaxies are more massive and more actively forming stars, then they produce more ionizing radiation, potentially speeding up reionization. Alternatively, if much of the star formation is hidden within dust, that dust absorbs the ultraviolet photons before they can escape to ionize the surrounding gas, potentially slowing reionization. Determining which scenario is correct requires careful analysis of galaxy properties, dust content, and the escape fraction of ionizing photons, quantities that Webb's observations are beginning to constrain. The temperature of the intergalactic medium evolves as well, heated by reionization, cooled by the expansion of the universe, heated again by feedback from galaxies. This thermal history affects how gas flows into galaxies, how efficiently it can cool and form stars, creating another feedback loop between galaxies and their environment. If the early universe had more vigorous star formation and more powerful feedback, the thermal history could differ from what we calculated, potentially affecting subsequent galaxy formation in ways our models have not captured. Cosmic rays, those high-energy particles accelerated by supernovae and other violent processes, fill galaxies and eventually escape into intergalactic space. The more star formation and supernova activity, the more cosmic rays produced, and these cosmic rays can influence gas dynamics, pressure, and ionization, adding another layer of complexity to the cosmic ecosystem. Every process connects to every other process, creating a web of interactions that defies simple analysis, demanding sophisticated simulations and careful thought about which effects dominate under which conditions. The philosophical implications reverberate through our conception of the universe and our place within it. We have constructed our cosmological narrative around a certain aesthetic, an expectation that the universe evolves from simplicity to complexity, that order emerges gradually from chaos, that there is a natural progression from primitive beginnings to sophisticated present. This narrative has deep roots in human thought, echoing evolutionary biology, historical progress, even creation myths where the world begins in formlessness and achieves structure through divine action or natural process. But the universe may not conform to our aesthetic preferences. It may not follow the orderly progression we find intellectually satisfying. It may be more chaotic, more contingent, more willing to violate our expectations of how things should proceed. The early rapid formation of massive galaxies suggests a universe more capable, more efficient, less constrained than we imagined. And this challenges our narrative not just scientifically but philosophically, forcing us to reconsider our assumptions about cosmic order and development. There is something humbling in this realization. We built models, invested decades of work into refining them, achieved remarkable agreement between prediction and observation across vast swaths of cosmic history. And then, when we finally gained the ability to see the earliest galaxies clearly, we discovered that our models fail in that regime. This failure is not evidence that science does not work but rather evidence of its power. We made predictions specific enough to be wrong. We built instruments sensitive enough to detect the wrongness. We have created a system of knowledge that can identify its own limitations and correct them. But the correction takes time and requires humility, the willingness to say we were wrong, to abandon ideas we invested our careers in, to start over with fresh perspectives. Not all scientists find this easy. There is natural resistance to paradigm shifts, natural tendency to defend existing frameworks, to argue that the anomalies are not as significant as they appear, that with minor adjustments the old models can survive. Sometimes this conservatism is justified. Anomalies sometimes do resolve under closer scrutiny, turning out to be instrumental artifacts or misinterpretations. But sometimes they do not. Sometimes they are real signals of new physics, new phenomena, new understanding waiting to emerge. Distinguishing between these cases requires careful judgment, openness to new ideas balanced with appropriate skepticism, willingness to question assumptions without abandoning all constraints. This is the art of science, the human element that no amount of data or computational power can replace. The data tells us what the universe does. But deciding what that means, what explanations are plausible, what new ideas deserve serious consideration, this requires human insight, creativity, judgment honed through experience and training. The coming years will test these skills across the astronomical community. As more data accumulates, as observations become more precise, as theoretical models become more sophisticated, we will gradually piece together a clearer picture of what happened in the early universe. There will be debates and controversies, papers claiming breakthroughs and papers refuting those claims, conferences where tempers flare and ideas clash. This is the messy reality of science at the frontier, and it is beautiful in its way, this collective struggle to understand, this willingness to engage in intellectual combat in pursuit of truth. We stand at a threshold. Behind us lies a century of cosmological progress, the development of the Big Bang Theory, the discovery of cosmic expansion, the identification of dark matter and dark energy, the precision measurement of cosmic parameters. Ahead lies unknown territory, new phenomena that demand explanation, new physics waiting to be discovered, new understanding that will transform how we see the universe. Webb has given us the key to cross this threshold, the observational capability to probe epochs previously inaccessible. But crossing the threshold requires courage, the courage to question what we thought we knew, to venture into uncertainty, to accept that our current understanding is incomplete. This is the situation where discovery happens. Not in the comfortable realm where theory and observation align perfectly, but in the uncomfortable space where they diverge, where contradictions force us to think more deeply. The massive galaxies Webb observes in the cosmic dawn are not merely objects to be catalogued. They are provocations, challenges thrown down by nature, demanding that we rise to meet them. They are saying, your models are incomplete, your understanding is partial, there is more here than you have grasped. And we must respond to that challenge not with defensiveness but with curiosity, with determination to understand, with recognition that being wrong about specifics does not mean being wrong about fundamentals. The story of the universe is still being written. Each observation adds a sentence, each discovery a paragraph. Sometimes we must cross out previous passages, revise what we thought we knew, acknowledge that our first draft contained errors. This is not failure. This is exactly how understanding grows, through iteration and refinement, through the interplay of observation and theory, through the collective effort of thousands of scientists each contributing their piece to the puzzle. What will the final picture look like? We cannot know from our current vantage point. But we can be certain it will be different from what we imagine now, richer in detail, stranger in its aspects, more beautiful in its complexity. The universe has a history of surprising us, of being more remarkable than our theories predicted. There is no reason to expect this pattern to change. Each time we develop new instruments capable of observing further or with greater sensitivity, we discover new phenomena. Each time we probe new regimes of energy or distance or time, we encounter surprises. Why should the early universe be any different? Perhaps, in the end, what Webb is teaching us is not specific facts about galaxy formation rates or stellar masses but something more fundamental about the nature of cosmic evolution and our ability to comprehend it. We are finite beings trying to understand an infinite cosmos. We have limited perspectives, limited data, limited cognitive capacity. We construct models that capture important aspects of reality but can never capture all of it, can never fully encompass the richness and complexity of actual physical processes operating across scales from subatomic to cosmic. Our models are approximations, useful fictions that help us organize observations and make predictions but should never be confused with reality itself. The map is not the territory. The model is not the universe. This distinction, obvious when stated explicitly, becomes blurred in practice as we become attached to our theoretical constructs, begin to think of them as true rather than as provisional approximations. Webb reminds us to hold our theories lightly, to recognize them as tools rather than truths, to remain open to revision when observation demands it. This epistemological humility is not weakness but strength, not uncertainty but wisdom, not lack of knowledge but recognition of knowledge's limits. And yet, within these limits, we achieve genuine understanding. We may not know everything, but we know much. We may be wrong about specifics, but we are right about many fundamentals. The universe does expand from a hot dense state. Galaxies do form through gravitational collapse. Stars do synthesize heavy elements. These are not mere theories but established facts, supported by overwhelming evidence, unlikely to be overturned by future observations. What we are revising now are details about timing, about rates, about the specific mechanisms by which these established processes occurred. Important details, yes, but details nonetheless, refinements to a picture whose broad strokes remain valid. This is the nature of scientific progress. We do not oscillate randomly between completely different worldviews. We converge asymptotically toward truth, getting closer with each iteration, each refinement, each new observation. The process is not linear or smooth. There are setbacks and detours, periods of confusion and controversy. But the overall trajectory is toward better understanding, more accurate models, more comprehensive theories. And we are on that trajectory now, working through the implications of Webb's observations, revising our models, moving toward whatever new synthesis will accommodate both what we knew before and what we are learning now. The early massive galaxies will find their explanation. Perhaps it will involve new physics, or perhaps it will involve better appreciation of known physics operating under extreme conditions. Perhaps it will require fundamental revision of galaxy formation theory, or perhaps it will require only careful attention to previously neglected processes. We do not know yet. But we will find out. The observations are in hand. The theoretical work is proceeding. The answer is out there, waiting to be discovered, waiting for someone to have the right insight, the right idea, the right connection that makes everything click into place. And when that happens, when understanding arrives, we will look back at this period of confusion and see it not as error but as necessary transition, not as failure but as growth. We will see that the anomalies were clues, that the contradictions were signposts, that the discomfort we felt was the discomfort of expansion, of mind stretching to accommodate new and larger conceptions of reality. We will be grateful for the challenge, grateful for the push beyond our comfort zone, grateful for the opportunity to participate in this moment of transformation. Because this is what we are witnessing, a transformation in cosmology as significant as any in the field's history. Not the overthrow of everything we know, but the maturation of our understanding, the refinement of our models, the deepening of our insight into how the universe actually works rather than how we imagined it should work. This is science at its best, confronting anomalies honestly, following evidence courageously, pursuing truth relentlessly regardless of where it leads. The James Webb Space Telescope floats in the darkness 1,000,000 miles from Earth, its golden mirror collecting photons that left their sources before the solar system existed, before the Milky Way achieved its current form, before most of cosmic history had yet occurred. Those photons, ancient messengers, carry information about a universe profoundly different from the one we inhabit, a universe younger, hotter, denser, more active, more capable of surprising us. We have built this telescope to catch these photons, to decode their messages, to learn what they can teach us about cosmic origins and evolution. The lessons are still being absorbed. The messages are still being interpreted. The story is still unfolding. But already, we know this: the universe was not what we expected. The early cosmos assembled its structures more rapidly, more efficiently, more dramatically than our careful models predicted. And in showing us this, in challenging our theories and forcing us to reconsider our assumptions, the universe is doing what it has always done. It is teaching us. It is expanding our understanding. It is inviting us to see more clearly, think more deeply, imagine more boldly. This invitation has always been extended to those willing to look, to question, to seek understanding despite difficulty and uncertainty. From the first humans who wondered about the lights in the night sky to the modern astronomers analyzing Webb's data, from ancient philosophers speculating about the cosmos to contemporary physicists calculating galaxy formation rates, we have been engaged in this same project, this same quest, this same reaching toward comprehension of the universe and our place within it. And now, in this moment, we touch the very beginning. We see galaxies as they were only hundreds of millions of years after creation itself. We witness the cosmic dawn, the epoch when light first conquered darkness, when structure first emerged from chaos, when the long story of cosmic evolution that would ultimately lead to us first began to unfold. These are not abstract observations. These are our origins being revealed, our history being uncovered, our deepest roots being traced back to their source. What we find there, in that ancient epoch, is a universe more potent with possibility than we imagined, capable of achievements we thought impossible, operating under principles we are still working to grasp. And this discovery, challenging as it is to our existing frameworks, is ultimately cause not for concern but for wonder. We live in a universe capable of surprising us 13 billion years after the fact, capable of confounding our expectations even when we have studied it carefully and thought deeply about it. We live in a cosmos rich enough, complex enough, mysterious enough to keep revealing new aspects of itself as long as we continue to look. This is the final lesson, the ultimate implication of what Webb has shown us. The universe is not a solved problem. It is an ongoing mystery, an endless frontier, a perpetual invitation to deeper understanding. And we, briefly conscious creatures on one small world, have been given the extraordinary gift of awareness, the capacity to look outward and wonder, the ability to build instruments that extend our senses across cosmic distances, the drive to ask questions about the fundamental nature of reality. The massive galaxies at the dawn of time shine across the eons, impossible and real, challenging and inspiring, mysterious and revelatory. They are speaking to us, these ancient structures, telling us that the universe was and is more remarkable than we knew, that our story is deeper and stranger than we imagined, that there are truths still waiting to be discovered by those brave enough to look beyond the comfortable boundaries of accepted knowledge. We are looking. We are discovering. We are learning. And in doing so, we are fulfilling the highest aspiration of consciousness itself, to comprehend, to understand, to know. The journey has no final destination. There will always be more questions, deeper mysteries, further horizons. But each step forward, each new observation, each revised theory, each moment of genuine insight brings us closer to truth. And that journey, that endless quest for understanding, is what makes us human, what gives meaning to our brief existence in this vast cosmos, what connects our small lives to the grandest story ever told, the story of the universe itself, unfolding across billions of years, revealing itself to those with eyes to see and minds to understand. The telescope watches. The data accumulates. The universe continues its patient revelation. And we, standing at the threshold of new understanding, prepare to step forward into whatever insights await us, ready to be surprised once more, ready to revise our theories once again, ready always to learn what reality has to teach us about itself and about the profound, beautiful, mysterious cosmos we call home.